I remember the first time someone told me that the most distant thing I could ever see with my naked eyes was not a star, not a planet, not even something inside our galaxy, but an entire galaxy on its own. And I didn't believe it at first because it sounded like the kind of statement people make when they want the universe to sound dramatic. But then I stepped outside, waited for my eyes to adjust, and realized the trick wasn't drama. It was patience. Your eyes don't work like a camera that snaps instantly. They negotiate with darkness. And if you give them time, they begin pulling faint signals out of the noise. And somewhere in that slow negotiation, a small, diffuse blur appears in the constellation Andromeda. Not bright, not impressive, just a barely there glow that you could easily mistake for nothing at all. And yet that is the entire point, because that faint smudge is Andromeda itself, a spiral galaxy larger than our own, sitting about 5 million light years away. What I like about this is how completely it violates intuition, because your brain keeps trying to shrink it. It sees something tiny and insists it must be tiny. But that blur spans roughly 220,000 light years across and contains close to 1 trillion stars, which is already absurd enough. But then you realize the light reaching you tonight left before humans built cities, before written language, before anything we would recognize as history, and suddenly you are not just looking at distance, you are looking at time layered into distance, which makes the experience feel less like observing and more like intercepting something that has been traveling longer than civilization itself. I sometimes think about this in a very mundane way. If you turn your head slightly, you stop seeing it. If you blink, you might lose it. And the fragility of that perception is ridiculous compared to the scale of what you're observing, because you are balancing an entire galaxy on the sensitivity of your retina. Andromeda dominates what astronomers call the local group together with the Milky Way. But even that statement hides something interesting, because we tend to think of our galaxy as the reference point, the main stage, and Andromeda as the neighbor, when in fact Andromeda is probably the larger system containing significantly more stars and extending far beyond the visible core that your eyes can detect. With binoculars, the faint blur stretches out, revealing a more elongated shape, and you begin to notice that what looked like a small patch is actually a vast structure whose outer regions are simply too dim for casual vision. And that's another quiet lesson. The universe is often bigger than what you see, not because it hides, but because your instruments, including your own eyes, run out of sensitivity. There is also something strangely personal about knowing that this is the most distant object you can see without a telescope, because it places a limit on unaided human perception. And limits are always interesting. They tell you where intuition stops working and where tools must take over. The apparent magnitude of Andromeda is around 3,6, well within the threshold of human vision under dark skies, which means that long before modern astronomy, long before telescopes, long before physics as we understand it, humans were already looking at another galaxy without knowing it, seeing a faint smudge and perhaps inventing stories, myths, or simply ignoring it, unaware that their eyes were already crossing intergalactic space. That idea sticks with me more than the numbers, because it means the universe has always been offering more information than we were ready to understand. And sometimes knowledge is not about seeing new things, but about recognizing what we've been seeing all along. Once you accept that the faint blur is an entire galaxy, the next uncomfortable step is realizing that it is not just another galaxy, but a larger one, and that quietly rearranges the mental hierarchy most of us carry around without noticing. because we tend to think of the Milky Way as the main structure and everything else, as distant decoration. Yet Andromeda sits there with a disk stretching roughly 220,000 light years across, compared to the Milky Way's to 120,000 light year span. And that difference is not cosmetic. It changes everything about how many stars can exist, how gravity sculpts structure, and how long the system has been evolving. Estimates suggest our galaxy contains a little over 100 billion stars, which already feels excessive, but Andromeda may host close to 1 trillion. And I always pause at that number, not because it's hard to understand mathematically, but because it exposes how poor human intuition is at scaling up. Once you pass a few billion, your mind stops picturing individual stars and begins dealing in abstraction. Yet gravity does not care about your intuition. It adds them all. Until the galaxy becomes heavier, wieder, and dynamically different. Another detail that fascinates me is that Andromeda is not floating alone. It has its own entourage, a system of more than 20 dwarf galaxies orbiting around it, and that immediately makes the situation feel less like two isolated islands and more like two archipelagos drifting in the same ocean. Among the best known are Messier 32 and Messier 110, and both carry signs of a messy gravitational history. Messier 32 appears compact today, almost like a dense remnant, and there is strong evidence that it was once larger, but repeated interactions with Andromeda stripped away much of its outer structure, pulling stars into tidal streams and compressing what remained into a tighter system. Messier 110 shows a different kind of story, with dust and traces of relatively recent star formation, suggesting it has not simply been sitting quietly, but has been stirred by gravitational encounters, reshaped slowly, like something molded not by a single dramatic event, but by persistent nudges over billions of years. When astronomers examine Andromeda's halo, they find streams of metal-rich stars that appear to have been torn from smaller galaxies. And I like that image because it removes the idea of galaxies as static objects. They are more like ecosystems, absorbing, reshaping, and redistributing material over immense spans of time. The stellar populations themselves reveal another contrast. Andromeda seems dominated by older stars, many more than 7 billion years old, and its overall luminosity is about 25% higher than that of the Milky Way. Yet paradoxically, our galaxy is currently forming stars at a faster rate, producing roughly 3 to 5 solar masses of new stars each year. While Andromeda generates closer to 1 solar mass annually, that difference suggests Andromeda had a more active past, building much of its stellar mass earlier, while the Milky Way is still in a comparatively lively phase of star formation. I sometimes think of this in terms of cities. One is sprawling and mature, filled with older neighborhoods, while the other is still expanding. Trains moving, lights appearing in new districts. Neither analogy is perfect, but it helps me hold on to the idea that galaxies have histories, rhythms, and phases, rather than a single frozen identity. And then there are the globular clusters, hundreds of them, around 460 confirmed in Andromeda, far more than the Milky Way hosts, and among them stands Mayal II, also known as G1, an enormous cluster containing millions of stars and shining roughly twice as brightly as Omega Centauri, the largest globular cluster in our own galaxy. Its structure is complex enough that some astronomers suspect it might be the leftover core of a dwarf galaxy that Andromeda absorbed long ago, which again reinforces the idea that large galaxies grow not just by forming stars internally, but by consuming smaller companions. The more you examine Andromeda, the less it feels like a distant blur, and the more it resembles a layered system shaped by mergers. See this, and long-term evolution, and at some point the comparison flips in your head. We are not simply looking at another galaxy. We are looking at a larger gravitational neighbor with its own history of growth, surrounded by satellites, filled with older stars, and quietly dominating its region of space. The moment you try to think about going to Andromeda, something curious happens in your mind. Because up to that point, the galaxy feels distant, but still somehow connected to the sky you see every night. Yet the instant you ask a practical question like, how long would it take to get there? The entire idea collapses into something almost absurd. And I like that moment because it forces you to confront the difference between seeing and reaching. You can see Andromeda with your naked eyes, but that does not mean it is accessible in any meaningful sense. And this gap between visibility and reachability is one of the most deceptive features of the universe. It looks close enough to point at, but the distance is about 5 million light years. And once you try to translate that into motion, you realize you are dealing with scales that resist everyday thinking. I sometimes start with a spacecraft we already understand, something like Voyager 1, which is moving at roughly 17 kilometers per second relative to the sun, an impressive speed by engineering standards, fast enough to leave the solar system and drift into interstellar space. And yet, if you aim something like that toward Andromeda and simply let it go, it would take on the order of 40 billion years to arrive. That number is not just large. It is longer than the current age of the universe, which is about 8 billion years. And I find that comparison useful because it removes any illusion that we are talking about an ambitious but achievable journey. Even if humanity built a machine and launched it today, it would not arrive before the universe itself had aged several times over. The destination does not just lie far away. It lies beyond the lifespan of cosmic history as we currently understand it. Then you might object, and this is a reasonable objection, that 17 kilometers per second is slow by cosmic standards. So let's imagine something extreme, something traveling at the speed of light. Light covers 1 light year per year, which is built into the definition. So reaching Andromeda at light speed would still require 5 million years as measured from Earth. That is already enough to make the journey feel detached from human timescale. But there is another layer, relativity. For the traveler, time would pass differently depending on the velocity and acceleration profile. And you could in principle shorten the subjective duration. Yet from the perspective of Earth and the destination, millions of years would still elapse. Civilizations would rise and disappear during the trip. Continents would shift. Species would evolve. And the spacecraft would still be en route, quietly crossing intergalactic space. I like to think about this not in terms of technology, but in terms of patience. Because patience is something we actually understand. Imagine committing to a journey that lasts longer than the entire history of human civilization, longer than the time since early hominins began using stone tools, longer than the period separating us from the last ice age. The scale stops feeling heroic and starts feeling detached, almost indifferent. The universe is not preventing us from going. It is simply not built around our preferred time scales. Distances between galaxies are not just large, they are structured in such a way that even light, the fastest signal available, takes millions of years to cross them. There is also a subtle psychological twist here. Because Andromeda is visible, your brain treats it like something within reach. The same way a mountain on the horizon looks like a day's walk until you try it and discover the terrain unfolding endlessly. The sky compresses depth, flattening millions of light years into a small angle above your head, and that flattening hides the true scale. When you restore the depth, when you allow the distance to expand back to what it actually is, Andromeda stops feeling like a neighbor. You might visit and starts feeling like a separate domain entirely. A massive structure, sharing the same cosmic neighborhood but separated by an ocean of space. So once you stop thinking of Andromeda as a distant blur and begin treating it like a physical system with structure, the first surprising thing is that we do not actually see it face on, which means everything we infer about its shape comes from interpreting an angled view, like trying to understand the layout of a city by looking at it from an airplane window tilted sideways. The disk is inclined relative to us, so its spiral pattern does not immediately reveal itself. Yet processed images and infrared observations begin to pull out the hidden geometry, and what emerges is a galaxy with two dominant spiral arms extending roughly 13,000 light years and traceable inward to about 1/600 light years from the core. These arms do not form perfectly smooth curves. They appear segmented, irregular, almost broken in places. And that imperfection is meaningful because it hints at gravitational disturbances, past interactions, and the slow reshaping of the disk over billions of years. Infrared data, particularly from space-based observations, show that these arms emerge from a central bar and intersect a large ring of matter, suggesting Andromeda is not just a classical spiral, but a system whose internal dynamics have reorganized material into rings, bars, and uneven arm segments, the kind of structure you expect when gravity has been tugging unevenly for a very long time. Then there are the globular clusters. And I find these particularly fascinating because they are like fossils of early galaxy formation. Dense spheres of ancient stars orbiting the outskirts like a halo of memories. Around 460 globular clusters have been confirmed in Andromeda, far more than in the Milky Way. And their distribution tells you that Andromeda has spent much of its history accreting smaller systems. Among them, one object stands out, Mael II, also known as G1, an enormous cluster containing millions of stars and shining roughly twice as brightly as Omega Centauri, the largest globular cluster in our galaxy. Its structure is complex enough that astronomers suspect it may not be a simple cluster at all, but the stripped core of a dwarf galaxy that Andromeda absorbed long ago. I like that idea because it transforms the halo from a decorative feature into a record of consumption, each cluster possibly representing something that once had its own identity before being pulled apart and incorporated into a larger system. When you think about hundreds of these objects orbiting the galaxy, you begin to see Andromeda less as a static spiral and more as a layered archive of gravitational encounters. But the most intriguing feature lies at the center, where expectations break down completely. In 1991, high-resolution observations revealed that Andromeda does not have a single bright nucleus, but two luminous concentrations separated by only about 9 light years. The brighter one, Lablet Bane, appears slightly offset from the galaxy's true center, while the fainter region, PDV, coincides with the position of a supermassive black hole. At first glance, this looks like a paradox, because galaxies are supposed to organize around a central gravitational anchor, yet here the brightest region is not exactly where you would expect it. One explanation involves a disk of stars orbiting the black hole on highly eccentric paths. In such a configuration, stars spend more time near the farthest point of their orbits, creating an apparent pileup of light away from the exact center. an illusion produced not by two separate cores, but by orbital dynamics. Another possibility is more dramatic. The structure could be the aftermath of a merger between black holes, where gravitational waves redistributed the surrounding stars and left behind an asymmetrical stellar distribution. Both ideas are physically plausible, and the fact that we cannot immediately distinguish between them is itself revealing, because it shows how even with modern instruments, the core of a nearby giant galaxy remains a puzzle. When you put these pieces together, the segmented spiral arms, the vast population of globular clusters, the possible remnants of absorbed galaxies, and the double nucleus surrounding a supermassive black hole, Andromeda stops feeling like a smooth spiral and begins to look like a system shaped by long-term instability, marchers, and internal reorganization. The closer you examine it, the less orderly it appears. Not chaotic, but dynamically alive, carrying evidence of past interactions embedded in its structure, as if the galaxy has been quietly rewriting itself for billions of years. There is a subtle shift that happens once you stop treating Andromeda as a distant object and begin thinking of it as something moving, because motion transforms distance into narrative. A galaxy sitting still is just scenery, but a galaxy approaching becomes a story already in progress. Measurements of Andromeda's motion, particularly its blue shift, reveal that it is moving toward us at roughly 110 kilometers per second. And that number sounds modest until you remember that galaxies do not accelerate like rockets. They drift under gravity, slowly but relentlessly, and when something as massive as Andromeda begins drifting towards something as massive as the Milky Way, the outcome is not a near miss, but an eventual merger written into the geometry of space between them. Careful observations, comparing stellar positions over many years, especially with instruments capable of resolving tiny angular changes, confirm that this is not just radial motion, but a genuine approach. And simulations based on those measurements suggest that in about 5 to 5 billion years, the two galaxies will begin a prolonged gravitational encounter. I like thinking about this in very undramatic terms, because the word collision misleads people into imagining something explosive, like two solid objects smashing together. When galaxies are mostly empty space, stars are separated by enormous distances, so direct stellar impacts are extremely unlikely. Instead, what actually happens is more like two swarms of fireflies drifting through each other. Their paths altered not by hitting, but by gravity reshaping their orbits. Spiral arms stretch. Tidal tails form. Stars are flung into new trajectories. And the once orderly disks distort into elongated structures before eventually settling into a new configuration. The process unfolds over hundreds of millions, even billions of years, which means that from any single moment inside it, nothing feels sudden. If you could watch from afar, you would see the galaxies approach, distort, pass through one another, separate slightly, and then fall back again, repeating the dance until their structures dissolve into a single merged system. What interests me more than the large-scale choreography is what this means locally. For something like the solar system, simulations indicate there is roughly a 50% probability that our solar system will be pushed into a region significantly farther from the galactic center than it occupies today. Perhaps 3 times the current distance. That does not sound dramatic, but it would change the sky completely. The familiar band of the Milky Way would stretch and warp. Andromeda would grow from a faint smudge into a sprawling luminous structure dominating the night. And over millions of years, the distinction between the two galaxies would blur. There is also an estimated 12% chance that the solar system could be ejected entirely from the merged galaxy, drifting into intergalactic space, no longer bound to the central mass. That possibility feels strangely quiet rather than catastrophic, because nothing would explode. The stars would simply thin out, the night sky gradually losing its density until only distant galaxies remained. Another interesting aspect is that this event is not accidental in the everyday sense. The Milky Way and Andromeda dominate the local group, a gravitationally bound collection of galaxies, and over long time scales, gravity pulls such systems inward. The smaller galaxies orbiting both giants are expected to join the merger as well, gradually folding into the same structure. From a sufficiently distant perspective, what looks like two separate galaxies today is already part of a single evolving system, slowly reorganizing itself. The idea that galaxies collide is not unusual. It is part of how large galaxies grow. What feels unusual is simply that we can identify the specific partner and the approximate timeline. If you step back from the details, the most striking thing is that nothing about the night sky is fixed. The faint blur you see today is not just a neighbor, but a future participant in a gravitational encounter that will reshape both galaxies. The motion is slow enough to feel abstract, yet precise enough that we can calculate it. And that combination gives the situation an odd calmness, as though two enormous structures are already adjusting their trajectories long before anything visibly changes. There is a curious misconception hidden inside the idea of a future galactic merger, because once people hear that the Milky Way and Andromeda will collide in roughly 5 billion years, they instinctively imagine that this event defines the fate of Earth, as if the real drama lies in the gravitational encounter itself. But when you place the timeline carefully, something quieter and more decisive appears first. Long before the galaxies begin to distort each other, the sun will already be changing in ways that matter far more to us. Stars like the sun do not remain constant. As hydrogen in the core is gradually converted into helium, the core contracts, the outer layers respond, and the luminosity slowly increases. This is not a sudden flare, but a steady brightening. And over hundreds of millions of years, even a modest increase in solar output begins to alter planetary climates. Estimates suggest that within roughly 5 billion years, the sun will be bright enough to trigger a runaway greenhouse effect on Earth, evaporating the oceans and filling the atmosphere with water vapor, which in turn traps more heat, accelerating the process in a feedback loop that does not easily reverse. I find this particularly striking because nothing dramatic needs to happen externally. No asteroid, no nearby supernova, no galactic disruption. The same star that made life possible gradually shifts conditions until liquid water can no longer persist on the surface. The oceans thin, clouds change, weather patterns destabilize, and eventually the planet transitions into something more like a hot, dry world with a dense atmosphere dominated by greenhouse gases. By the time the Milky Way and Andromeda begin their visible gravitational interaction, the sun may be up to 40% brighter than it is today. And Earth, if it still exists in recognizable form, will already be hostile to the kind of surface life we are familiar with. That rearranges the narrative in an interesting way. The galactic collision becomes visually spectacular but biologically late, arriving after the more subtle transformation driven by stellar evolution has already reshaped our environment. Meanwhile, the solar system itself will continue orbiting within the Milky Way as the gravitational pull from Andromeda grows. As the galaxies approach, tidal forces begin stretching their disks, and stars are gradually nudged into new trajectories. The solar system's orbit around the galactic center is not fixed. Over billions of years, it can migrate outward or inward depending on cumulative gravitational interactions, Simulations suggest a roughly even chance that we could be pushed farther from the galactic core, perhaps into a region where the night sky looks less crowded, or into a more elongated orbit around the merged structure. There is also a smaller probability that the solar system could be ejected entirely, drifting into intergalactic space. No longer bound to the final galaxy, none of these scenarios involve collisions between stars. The distances remain too vast. Instead, the transformation is geometric. The paths of stars, reshaped by the evolving gravitational landscape, as the merger progresses, the spiral structures of both galaxies are expected to dissolve, their ordered disks disrupted, and eventually settling into a new configuration. Simulations often suggest that the final result could resemble a giant elliptical galaxy, though the exact outcome depends on how much gas remains to form new stars. If enough gas survives, the merged system might retain some disk-like features, perhaps even evolving into a lenticular galaxy or a massive spiral over extremely long timescales. The smaller galaxies of the local group, those orbiting both the Milky Way and Andromeda, would gradually fall inward and be incorporated into this larger structure, completing a slow consolidation that unfolds over tens or even hundreds of billions of years. From afar, what begins as two spirals would eventually appear as a single, more rounded system, with streams of stars marking the memory of the merger long after the initial encounter. When I think about this sequence, what stands out is not the violence, but the patience of it all. The sun brightens, Earth's oceans vanish. Stellar orbits shift, galaxies stretch and fold, and none of it happens on a timescale that resembles human experience. The transformation of our local cosmic environment unfolds as a layered process with stellar evolution, orbital dynamics, and galactic interaction, all contributing at different moments. Gradually, replacing the familiar sky with something entirely new. When I think about Andromeda after everything else, the size, the distance, the future merger, I end up returning to something quieter, almost philosophical. Not because the science runs out, but because the science itself pushes you there. You are looking at light that left 5 million years ago. Which means the Andromeda you see is not the Andromeda that exists now. And the gap between those two versions of reality becomes strangely personal. The photons reaching your eyes tonight began their journey long before humans understood what a galaxy was. And during the time they traveled, life on Earth changed dramatically. Species appeared and vanished. Ice ages came and went. Civilizations emerged. And all of that unfolded while the light kept moving, indifferent, uninterrupted. So when you look at that faint smudge, you are not just observing distance. You are intercepting a message that has been in transit longer than human history. And the unsettling part is that whatever is happening there now is still hidden behind millions of years of delay. That time delay changes how you think about existence elsewhere. Andromeda contains roughly 1 trillion stars, perhaps 10 times more than the Milky Way. And even if the probability of life emerging around any single star were extremely small, multiplying that small probability across such an enormous number of systems shifts the question from speculative to statistical. I find it difficult to think about 1 trillion stars without wondering how many planets formed, how many cooled, how many developed oceans, how many hosted chemistry that slowly became biology. On Earth, life appeared relatively early, once conditions stabilized. And over billions of years, it evolved from single-celled organisms into complex ecosystems, and eventually into beings capable of reflection. If that process is not unique, if it can occur whenever conditions allow, then Andromeda has had more than enough time and more than enough opportunities, its stellar population is dominated by older stars many billions of years old, which means planetary systems that may have enjoyed long periods of stability, entire evolutionary histories could have unfolded long before Earth formed. Civilizations could have risen, observed the sky, perhaps noticed the Milky Way as a distant spiral, and then vanished, leaving no trace that could reach us in time. I sometimes find this idea more humbling than the sheer size of the galaxy, because it suggests that intelligence, if it appears elsewhere, may be separated not only by distance but by epochs. A civilization in Andromeda might have flourished and disappeared millions of years before the light we see tonight even began its journey. Another might exist now, but its signals would take millions of years to arrive. The universe becomes less like a shared present and more like overlapping layers of time. Each region living in its own era, barely aware of the others. And yet, despite this separation, we can infer structure, mass, stellar population, and dynamics from here on a small planet orbiting an ordinary star near the outskirts of a galaxy that is itself overshadowed by a larger neighbor. That contrast always strikes me. Physically, we are insignificant, but intellectually, we are not confined to our immediate surrounding. We measure galaxies we cannot reach, estimate events that will occur billions of years after we are gone, and reconstruct histories written in light long before humans existed. The more I think about it, the more Andromeda stops being just a destination or a future collision partner and becomes a mirror for perspective. It shows us the past through delayed light, the future through gravitational motion, and the present through the act of understanding the universe is not static. Galaxies move, matter evolve, and eventually redefine the large-scale environment in which stars and planets exist. Against that background, Earth is a tiny grain of dust, and human life is brief, but the ability to recognize that smallness changes the story. We are not just inside the universe. We are part of the universe that has begun to examine itself, calculating distances measured in millions of light years, imagining civilizations that may never meet us, and tracing events that unfold long after our own timeline fades